another strong effect. Here are three hydrogens right next door to this carbon double bond oxygen. What do we know about carbon-oxygen double bonds?
Be very polar.
Very, very polar. And so we see a pretty strong effect down, even though these hydrogens are not directly attached, I've got that very polar bond there, so I'm down beyond 2. But look at the carboxylic acid, the hydrogen on the OH, way downfield. And I've griped about this before, but for some reason or other, we only run from 1 to 10 on the downfield shifts, and carboxylic acids are usually between 11 and 12. And so we tend to show them as offset peaks. Notice it says this is offset by 2 parts per million, so it's down here about 9.8, I'd say. So that means it's where, really? 11.8. They actually, and I don't know why, it seems insane to me that you wouldn't just run the scale down to 13 and just show everything on scale, but this is very typical. So that even though, because this is beyond the 10, they just show it 2 points or whatever it is, someplace on the scale and tell you what the offset is. Okay. Again, carboxylic acid is about the only thing that signal that far downfield. Another thing that we look at in NMR that's important to us is recognizing the equivalence of protons, because this tells us how many signals we expect to see. These 3 methyl groups are identical to one another because they're attached to the same carbon. And remember, because of rotation around this bond here and rotation around each of these 3 bonds, these hydrogens experience the same environment. So they're identical to one another. So they appear as one signal. These 3 hydrogens over here are identical to one another, and they appear as one signal. And so when you're looking at NMR spectra, you need to recognize the equivalence of hydrogens. How are we doing? By the way, this peak is a lot bigger than that peak. What's up with that?
Integration.
It should be a 3 to 1 difference in area under the signal, because the number of hydrogens signaling is reflected in the size of the peak area. Okay. Here's another one. These 3 methyl groups here are identical to one another. These 2 hydrogens here are identical to one another, and these 3 hydrogens here are identical to one another. So we see 3 distinct signals. And the signals, again, are reflect the amount of shielding or de-shielding that these compounds might be experiencing. Now, we would expect C to be farther downfield for what reason? Here's the C hydrogens.
The oxygens.
Because they're adjacent to 2 carbonyl groups that are polar. Does that make sense? Whereas these 3 are adjacent to 1, so it's not as far downfield. These are fairly removed. There is this oxygen right here, but these guys are a couple of bonds away from that. So they're a little bit downfield, but not very much. Does that make sense? And in the end, when you're using NMR to rationalize a structure, it ought to be consistent from this kind of analysis perspective. All right. Now from table 13.3, which we're not looking at anymore, predict the downfield or chemical shifts of the protons in the following compounds. And let's just do it qualitatively here. Where do we expect this guy to appear? 11 or 12 in that range. Where do we expect these hydrogens right here because of the chlorine here? We might expect these down 2 or 3, right? Does that make sense? These not so much, because now it's 2 carbons away from the chlorine. These will be relatively unaffected. It's a proximity thing. It's kind of like horseshoes.
So there's going to be 3 peaks in B on the
Yeah, all 3, and they won't be simple peaks. They'll split each other. We've not talked about that yet, but just based on position. And over here, I've got a double bond, so we expect considerable downfield shift here and here for B and C because they're different. And then the A's will be downfield a little bit, but not much. Does that make sense? Again, it's a proximity thing. And we could go to the tables and get accurate values, but let's look at our predictions and see how they did. The carboxylic hydrogen, between 10 and 12, the experimental value in this case is 11.4. If I, and by the way, the methyl group up here, because it's next to the carbonyl group, down about 2.1. For compound B, we expect the carbon bearing the chlorine to be downfield between about 3 and 4, it's 3.7. The protons on B are about 1.7, and the regular ones, the methyl groups, about where they're supposed to be, about 1.0 is what they say. And on the compound C that we're looking at here, the methyl protons are pretty much unaffected. They would be normally at 0.9, they're at 1.0. The vinyl protons B and C should be between 5 and 6, and that's in fact where we find that range. Does that make sense? The intensity of the signal, again, reflects the number of hydrogens hiding under the signal, or represented by the signal. And in the case of the molecule, or a molecule much like what we were looking at before, we've got 9 here and 3 here. Older instruments used to integrate the signal like this. There would be a drifting line here, and as soon as this starts to go up, this is counting the area. This is actually, this jump is proportional to the area under the peak. Okay, it's an integrator. And so we see about 2 units here. This thing jumped, and we see a jump of 6 units here, and that's a 3-to-1 ratio, which again is proportional to the difference in the number of hydrogens in the signal. You don't see this kind of integration as much anymore. Yeah.
Well, like an exam, you would continue to give us?
I could
at least
give you
some
that, but
information?
I'd expect you to recognize what that represents.
Like
Or-
usually like it's like 6,000.
Yes, and I'll often give you the integration as well. But I would expect you to be able to do this.
Or at
Yeah.
least recognize that if you give us areas, what the values were.
Yeah, now if you've got the little drifted line, you can just sit down and measure it and say, oh, this goes up 3 units and this goes up 5. That's a 3-to-5 ratio. Your structure should have a proton 3-to-5 ratio that befits that. Okay? The problem with this is it doesn't tell you if this is 1 hydrogen to 3 hydrogen, or 3 to 9, or 4 to 12, or whatever. This just tells you the relative ratios. Now, the big deal in NMR is the spin-spin spin. And this takes a little time to go through, but this is where the power of the technique really emerges. It turns out that a hydrogen signaling in the NMR is affected by its downfield shift, its electron environment. It's affected by the strength of the magnetic field applied to it, and it's also affected by what's going on next door. In other words, if there are protons next door also experiencing the applied magnetic field and responding, they create very, very weak magnetic fields themselves that either can strengthen or weaken the applied magnetic field I experience. Does that make sense? And that's the basis for spin-spin-split. So, look at this guy. This is a pretty good example. I've got a 2-carbon compound, and I've got 3 hydrogens here experiencing the magnetic field, and we've got a fair amount of downfield shift because of the bromines present. So we actually have good separation between the 2 kinds of hydrogen, type A and type B. But notice that they don't split cleanly into simple peaks. They appear as multiplets based on what's next door. Now these guys, overall the area under this double peak here should be twice the area under this triplet here. But what's of interest to us here is the splitting pattern. Okay? In general, we're going to apply the n+1 rule. If there are n hydrogens next door, I'm going to appear as an n+1 peak. So if there's 1 hydrogen next door, I'm going to appear as a doublet. If there are 2 hydrogens next door, I'm going to appear as a triplet. This allows us, this gives us a window to get some insight on the connections in the molecule we're looking at, how things are located relative to one another. Okay? And we're going to look at that here in grand detail. Let's look at the A protons here. Actually, the B protons is what we're looking at first. These guys are signaling here, and they can experience next door one of two states. The hydrogen A can be aligned with the magnetic field, in which it will move, if they are, they'll move the peak upfield. If they're downfield, they will oppose the magnetic field and they'll be shielded just a little bit. So what's happening next door affects what I experience. The effective magnetic field, if the hydrogen next door is aligned with the magnetic field, is greater than it would normally be. And if they're opposed, it would be weaker than what it normally would expect it to be. And what the applied magnetic field really is right in the middle. It's the average of the two. But this is going to be split into two states because there's a probability of half of them being aligned with the field and half against the field. Does that make sense? And so I'll see it double. So the two possible spin states next door. Does this make sense? You should have seen this before. Right. I don't want to bypass this unless I think everybody's on board with this. Okay, it's what goes on next door affects what I experience. And there's two possible spin states for one hydrogen next door. I'm going to show us two spins or two peaks because of that. It's a small difference, but it's there. Now, if I look at this guy, what it shows, there are two hydrogens that can exist in several states. They can both be aligned with the magnetic field, both opposed or split. Okay, so there's actually three spin states that are possible next door of two hydrogens. Does that make sense? So I've got this where they're both aligned with the magnetic field next door. Here where they're both aligned against the magnetic field. This is going to make me shift downfield further. This is going to take me upfield. And if they're anti to one another, they're going to have no effect. And that's going to be where the peak really ought to be without the hydrogens next door. Does that make sense? Notice that there's two ways for this to occur. Okay, I've got that and I've got that. And so the probability of them being split next door or being opposed to one another next door, twice as probable as having either one of the other states. So the middle peak will be bigger. More likelihood of that. And so the triplet will have two small peaks and a big middle peak. I'm saying a lot of words and I'm not saying a whole lot of... Are you following what I'm saying here? Okay, three possible spin states next door. Both against, both for, and a more likely where they're both split in two possible ways. Does that make sense? And that's what, so I'm going to show as a triplet, with the middle peak being the most likely biggest peak in area. And that's what we'll expect to see. If I have three hydrogens next door, there will be four spin states possible. Three against, three opposed, and various split forms where I've got all three of them doing different things. Does that make sense? And that will create a quartet. That's the n+1 rule we were talking about. Now, the n+1 rule is sort of amplified here in this diagram where Pascal's triangle was mentioned. Because Pascal's triangle approximates how the peaks will look in terms of their ratios. Everybody understand Pascal's triangle? Seen it before? What I do, I take that and that, and I get that. If I add that to that, I get that. If I add that to that, I get that. So any pair of numbers combined will give the number directly below it. And you say, well, isn't that fascinating? But what has that got to do with what we're talking about? But it gives us the likelihood of the peaks So if I've got a triplet, it'll be in a 1:2:1 ratio. If I've got a quartet, it'll be in a 1:3:3:1 ratio. In other words, this gives us an approximation